Good morning, everyone. Welcome to the second day. Yeah, I heard we're going to speak about BOTracle. What is BOTracle? That is audio.
Yeah, hi. Thank you.
Okay, so I think you need to use this as a microphone.
Okay, sure. Thanks. Yeah, hi everyone. Thanks for attending. My name is Jan. I'm a computer scientist at Adobe, and we did some research on bot detection. And what we came up with is the BOTracle, framework for discriminating bots and humans. Let's start. So, why would we care about bot detection? I mean, the internet is there, traffic is there. Why would we care? What's the issue with bots? From a security standpoint, there are many issues. Bots can be used for scraping, they can collect data, they pose privacy risks, they can be used for fuzzing, security, testing out security bugs, cross-site script testing, probing, whatever. There are so many issues, and I think these images visualize it very good. I mean, for example, social media is full of spammer bots. It's super annoying. You can't enjoy it. And for a company like Adobe, it's especially of interest because these bots decrease the user experience, and they could cause a decrease in revenue or something like that. And next to the security perspective, also this perspective is relevant to companies or institutions that host applications that are available in the internet. So in order to get started, we wanted to first analyze what's out there in the market, what has been done so far by researchers and other companies to tackle the issue of bot detection. You all know it's CAPTCHA. It's not very interesting anymore. Technology is advanced. These CAPTCHAs are solvable by machine learning algorithms. There, for example, reinforcement learning approaches using convolutional neural networks that can solve credentials with confidence. And even the more easier way is to simply pass the CAPTCHA challenge to a CAPTCHA farm, which is a data center where human operators solve the CAPTCHAs for a fee. This is a business model and also done in the wild. Human systems part is also heavily impacting users because solving a CAPTCHA can be challenging sometimes. We're not sure where does it stop. I personally always thought of this, and this is simply not appropriate anymore in the year 2024. Also, there are classifiers without client interaction. We separated the approaches into challenge-based approaches, which is simply CAPTCHA, edge CAPTCHA. I mean, there are so many variations. There are classifiers don't require any connection. There are some heuristic-based classifiers, regression models. There are so many, but many rely on the same problem, that labeling the actual data to know what is an actual condition to identify a bot. Thanks. So it's quite challenging, and it's really domain specific. For example, on an e-commerce site, people would say, okay, the bot is someone that, or a human is someone that purchases an item, but as the figure shows, PS5 enthusiasts would probably disagree because there were many scalper bots that purchased all the PS5s, so they went out of stock, and humans were slow to actually buy them. So, and then maybe the reputation of an online shop would be damaged and not acceptable to many shop hosts. And what would be the definition of the bot? And this gets really tricky. What if bots start buying products? What if I want to protect a non-e-commerce site? For example, if I have Instagram, for example, it's a social media, you can't purchase anything on there, but still it's affected by bot traffic. So we need some more generalistic definition of what is a bot, what is a human to start labeling. I mean, and we also have to think about the assumptions that we're making, that they are probably not catching every bot, but it's relevant that we ensure that we don't misclassify a human as a bot, because catching bots can be enhanced on basis of these assumptions. But first, some takeaways from the related work section. Bots cause many problems. The protection mechanisms can be circumvented, and there is no general purpose method of bot identification because of the previously mentioned problems. And we came to the conclusion that bot detection is highly domain specific, depending on the application of your website or entity you're hosting or exposing over the internet. So let's come to our approach. How can we improve the detection? So first, we were given a scenario of an e-commerce website with roughly 50 million monthly active users. And then we first made some assumptions that on this page, bots and humans behave differently when using resources, or generalizing this assumption, they behave differently when using the internet. For example, bots will work very repetitive, very fast, humans or very deterministic, and humans are some more non-deterministic. Some people will stare at a product for longer, some for shorter, so there is some randomness. Bots will try to obfuscate their identity because they don't want to get caught, at least the bad bots. And but what we noticed that the bot objective can not really be obfuscated. A scraper bot will always try to collect as much data as possible. A scalper bot will always try to buy as many products as possible. And this is the weakness of bots, the inherent weakness that can't be obfuscated. And so we created or stated the hypothesis that bots and humans can be discriminated via these behavioral differences. And the goal we set ourselves, identify as many bots as possible without disturbing human users. So just the scenario again. From this website, we took a data set with roughly 800,000 data points with 103 features. The data was extracted using Adobe Analytics, so it's actually an actual customer. And then the clients could be recognized via fingerprinting. Maybe Adobe is not the most privacy friendly company, but this was the data we were working with. And so first we tried to identify useful features on which we could base the assumptions in data that could also be applied to other data sets as well. Then we were trying to label a subset of these data points using these assumptions, and then convert the data into suitable representations, train machine learning models in the data, and try to catch the bots. So when we went through the data, we could start creating categories of features. So there are identity features, technical features, traversal visit and interaction features. Some examples of these features are below. And then in the third row, we can see where we use the features in which part of the detection approach. So, but first, before presenting the approach, I would like to talk about these assumptions we made that we think is quite generally applicable, because we say that a bot is each line or each line is labeled as bot if its IP address matches the IP address of a publicly known data center of cloud providers, because who in the world would use a cloud VM to browse the internet? And also we say that people using proxies that might proxy via these cloud data centers are also not in our interest. We would like to maybe throttle traffic or restrict the traffic coming from these sources, because this is not in the interest of the company. And a human is labeled, or a client or a user is labeled as human if it's not a bot, and it can be linked to an event that can only be triggered by an associate of the affected entity. So the entity is maybe the network, the website, something that we want to protect. And the event could be, for example, on an e-commerce website, it could be a purchase made by a website employee. For example, if I go to Adobe and, for example, create a subscription for my personal use, they will know that I'm affiliated with Adobe. And with this customer of Adobe we had and analyzed the data set, this was an e-commerce site. And luckily, the employees were also buying products from these e-commerce sites or the site. And then we could use their behavior or their data, we could label them and then start expanding this data using machine learning. This was the whole concept. And we could learn, okay, this is how employees of the website or the entity behave. And we know they are humans. And then we would start extending the set of humans by looking at the behavior of the known humans and then comparing it to behavior of unknown users. So, but of course, there are limitations. Humans could use entity associates could automate their browsing. But I think these limitations are quite rare and we can work with that. Oops. Direction. So before coming to the actual learning or machine learning approach, we thought about having suitable data representations because we didn't do much about the machine learning models, but we wanted to improve the detection performance as much as possible. And then, you know, the saying garbage in, garbage out, we wanted to prevent that. So the individual hits or web requests were encoded as were one-hot encoded, but as this is a sparse data set, we had to do some trick to make this more dense and reduce the sparsity of the data set. And then we combined rare categorical values into a single vector. This is and this is also why you will see later on the actual data in the feature names. And then we came up with our own concept of website traversal graphs. We aggregated, so as we were applying fingerprinting, and we knew we could re-identify the users in the data set. And then we assumed, okay, in a subsequent request stream of where each request occurs within 30 minutes, this is a session. And then we aggregated these sessions into these graphs and then started visualizing or connecting these requests into a traversal graph, which shows how a user has traverse the website. For example, here, the user started at the home page, and then he went to the auto page, then did some search, looked at some key, which is product page. So this person or this user looked at the in this example, yeah. Then the same or requests on the same page were aggregated into the nodes. So each node was extended with a feature vector, which was also one-hot encoded. And these feature vectors included the page type, hits per page, average time between hits per page, and so on. So a lot of graph metrics, which we then fed into the machine learning model. Yeah, and then basically this is the detection pipeline, which we wanted to use in inference. So on training, we trained each model separately, but after shipping this to production, we would then sequentialize the models because heuristics are cheap to compute. It's cheaper than inference of some models. So we want to catch the low-hanging fruits, the easy detectable bots using the heuristics, and the more tougher ones using the semi-supervised general network. And yeah, if we have a classification, then it exceeds our confidence parameter lambda, then we push the classification. Otherwise, we start analyzing these sessions and actually analyzing the behavior, the browsing behavior. And finally, there's this dotted decision engine, which then on basis of the classification we made would probably throttle the API traffic or the website traffic so that these clients would, for example, receive a captcha or some other challenge because we assume that they are bots, and then we want to make their browsing experience worse or even more expensive, or we would simply throttle their requests because bot requests are not wanted on this page or on the entity we want. Yeah, so again, the length criteria on inference, we would also include this in the heuristics, but for training, we would actually exclude this. Yeah, and then we came up with 4 heuristics, which we thought are sense, which we could also in the yeah, so the first one is checking for forged user agents, where we applied browser duck typing. which is a technique that tests for certain features of a browser. For example, in Google Chrome, there will be a value set to window.chrome. And if this value is present and other duck typing methods failed, then we can assume that the browser is Chrome. But if we see the user agent is not equal to that, or the other way around, someone brings us a user agent, says, hey, I'm the client, I'm using Google Chrome, everything's fine, but we're missing this attribute. We know he must have forged the user agent. We didn't sign a bot. Normal humans wouldn't change their user agent. We have these where we check the frequency of the users browsing. So how much time does it take to go from page 0 to page 1, from page 1 to page 2. And if these times are very similar, this is also an indicator for automated traffic. And if this is consistent over all requests, then we can also flag this as a potential bot. Then, some not so dedicated bot developers forgot to replace the user agent. Then there were some keywords in the user agent, for example, Go HTTP client, which is a strong indicator for automated browsing. This is also flagged as bot, and then unrealistic window sizes. If a browser is simply too small for a human to properly use it, then we can assume that this is also some sort of bot activity, because some bots use very small browser sizes to then apply, because they apply some CNN automation, and this is much less expensive when the resolution is small. This was the again, we didn't change anything about architecture, so we just did all my time readings. Same for the deep graph convolutional neural network. There's one thing I want to mention. And now approach, when initialized with DGCNN, you have to set the parameter k, which is a constant that will cause the feature vectors of the nodes of. And we use all the personal graphs that we analyzed, and we set this to the highest value. So the largest graph was 35 nodes, and then we set this value to 35 to ensure that we don't cut off any features that we have. So, but if the graphs grow very large, it might make sense to off features to make this more efficient, economically efficient. Let's come to the evaluation part. So this was then the data set up ground assumptions. From this 800,000 data points, we were able to identify 51,000 bots, where the IP address was of the bots was known on the list of the known IP addresses of the data center, and then also 7,630 data points were we were able to connect to employees or associates of the webs, the data sets we analyzed. Then we apply heuristics I introduced before, and on first sight, this might not be the most promising, but actually the high precision means that most predicted bots were actual bots, which is quite good, because the heuristics didn't misclassify many humans as bots, which is totally something we want to totally avoid. And low recall means that most actual bots were not predicted as bots. This means that using heuristics alone is not sufficient at all. But again, this was only intended to catch the low-hanging fruits, the easy to detect bots, so this was acceptable to us. The more interesting part starts here now. The semi-supervised generated adversarial network performed really well. The training was done on one part of the data set. I think the split was 70-30 or 50-50, not sure. I think it was 50-50 for the SGAN and 70-30 for the DGCNN. The evaluation was only done on some test data. We can see the values are pretty good. I mean, we have a high score, high accuracy, and precision, and the discrepancy between training and test data is also very low. This means that the model generalizes kind of well. We can also see high or good precision recall curve, and the ROC curve is also high, which indicates for good classification performance. And then we analyze which features were actually most responsible for the detection, which is the browser height, which also we used for the heuristics. And then the feature post Java enabled. This is some duck type probing we did because some clients said they are the Internet Explorer, and the Internet Explorer is the only browser that supports Java applets execution. But once the client received the duck typing probe, it was clear that the browser couldn't execute the probe, and this is also a sign that the user agent is. And then rare user agents were also, so user agent other is where all rare user agents were combined into this one vector to keep the data metrics more tight. And yeah, basically it. Then GCNN, we applied, so when we computed the sessions, the data set was highly imbalanced. We applied overlap clustering, and if the overlap coefficient was over 0.9, then we would label the unknown graph as human. So we could balance out the data set more. And here we also achieved great results. Yeah, and again, the model also generalizes very well with numbers for the test evaluation. And we also compared on the same data set another approach, which is called BOTracle, because this was also implemented by a colleague of mine. And we were able to achieve on-par results with BOTracle, which is good. Yeah, so does the size of the WT graph matters? Yeah, sort of. We see 100% classifications, but this is somehow caused by only having one class for the bigger graphs, but we can see good results for small graphs as well. But this doesn't mean it's only a single request. This means that only a single page was visited. Yeah, again. So are the results good? We wanted to have some comparison of our research with someone else, but it's quite hard because we have a confidential data set. But then we found this report from a cybersecurity company named Imperva, and they found similar results. They said that the internet traffic consists of 42% bots. We found 41%, so there's only a small deviation, which increases the confidence in our results. Yeah, limitation. Yeah, ground truth assumptions could be wrong for sure. We could always do a mistake. There could be always some race conditions, but this is, I think, something we have to accept. And this also the risk of misclassification due to these assumptions becomes lower when designing an approach that is highly tailored to a domain-specific entity to be protected. BOTracle is unable to detect bots that perfectly mimic human behavior. But this is acceptable to us because this will kill all benefits of bots. Bots are fast, bots are automated, bots can do a lot of things in a short amount of time. This is something which humans cannot do, but this behavioral approach forces bot operators, if they still want to operate their bots, to mimic human behavior. So this will limit the economic profitability of their bot operations, which eventually will lead to them to stop creating bots. Yeah, and sadly, we could only evaluate on a proprietary data set. Limited benchmarking was possible, but we compared with BOTracle, which is also a publication, and we received on-par results, which gives us confidence in our work. Yeah, in conclusion, yeah, bot detection certainly requires domain knowledge. The entities to be protected on the internet are very diverse, and it's quite hard to find a generalistic approach. But if this protection approach is tailored to the domain, we can achieve good results. Labeling assumptions should rely on non-obfuscatable features. We want to assume on the intention of the bot, and we also want to make realistic assumptions. And behavioral detection forces bot operators to mimic human behavior, which improves user experience for actual humans, because bots will, if they deviate from the human behavior, we will throttle their requests, we will make browsing harder for them. So this means that either the bot behaves like a human or it will get punished. This also prevents capture detection evasion via capture farms, because if we throttle their requests on basis of their behavior, there's no way to circumvent. And yeah, limitations exist, but increase cost and effort for bot operators. And we were quite happy with the results. And that's it. Yeah, thanks for listening.
For one quick question.
Okay.
Yeah. Question is about the heuristics. So my question is about the heuristics.
Yes.
What is the percentage of humans that were classified as bots by heuristics?
I mean, I don't have. I mean, there were some. I think 9 out of 7,000. So nine humans out of 7,630 were classified as bot. Yeah, and this is something, but we didn't. Yeah, basically that's the answer to your question.
Okay, do you think there is going to use also once you really substitute?
Maybe I didn't get. Oh, okay. Yeah, I mean, if economic viability is not an issue, we could simply skip the heuristics and only rely on the labeling assumptions. These heuristics were only designed to have some to increase the cost efficiency. But from a detection standpoint, I think it makes sense to only use the DGCNN. If money is not an issue, if you want to only focus on the behavior, and this will probably lead to flatter results and less misclassification because we have more data available. I mean, the heuristics only looked at one dimension of the whole data set, and for sure there is not enough knowledge to be very confident. But I think with the graphs, it's more effective here. Sure.
So, no more questions? Can you go back to your
Which slide? Can you say?
So can I just elaborate on this? The realistic assumptions. The realistic assumptions are relying on realistic assumptions for what this. How do you define this?
Yeah, I mean, that's sort of subjective, but I mean, most of us, so this realistic really means that, for example, the labeling assumption that we label a data point as bot if the IP address is linked to a data center public cloud provider. I mean, most of humans, like 99%, will probably not use the internet using a computer that has an IP address assigned to a data center of AWS, for example. I mean, you won't log into a Windows instance, for example, of AWS using remote desktop to browse the internet. It's too complex. Why would you do that? That's what we mean with realistic assumptions. Okay.
Okay.
Sure. Anytime.